Hello everyone. Through this presentation, we are going to discuss and answer three questions, and in this first part, we will try to explain and demonstrate how the computer technology developed from the first generation computers until now, in order to find a solution to a major mathematical problem, which is finding the largest existing prime number. And to give you an idea about this interesting topic, the largest prime number known so far was found via a supercomputer in 2018, and it equals to this number in front of you. Therefore, in order now to proceed, we need first to take a look at and describe the different changes in technology throughout all the computer generations, starting with the different technologies used to construct computers, from vacuum tubes to microprocessors nowadays, and moving on to the improvement of the memory, to finally describe the CPU's evolution and its components and technologies. Now moving on to the evolution of the architecture or the technology used in a computer, we have first the vacuum tubes, which were the first design of the stored program concept approach, which is mainly a computer that stores instruction in its memory to enable it to perform a variety of tasks in a sequence. The idea was basically the von Neumann model that of course we will discuss and explain later on this presentation, where the instructions are stored with the data in binary code. The first generation of vacuums was full of disadvantages, such as being unreliable, very costly and generating a lot of heat, and some examples might be the ENIAC, EDVAC or the IBM 750. The second generation was the transistor ones that were reliable, had smaller size, generated less heat, and faster compared to the vacuum tubes. And some examples are the following. The third generation was the IC one, where they were more reliable than the previous two generations, but also smaller, faster, needed less maintenance, and generated less heat. Also, it was the first generation to support high-level languages, and some examples are the known IBM 360 series, TDC 316, and the personal data processor. Finally, both the very large-scale integration generation and ultra-large-scale integration generation mainly implement the concept of microprocessors that contains a growing number of transistors, and they are very cheap, portable, reliable, and implemented new CPU technologies. The examples of later generation that implemented microprocessors are simply your current laptop, desktop, notebook, or supercomputers such as Cray 1. Now for instance, if we take the memory of the IS computer as opposed to the next memory technologies in the following computer generations, we could say that in the first generation memory, it contains storage locations called words of 40 bits each, and they were both data and instruction. A word may contain numbers with a minus or plus sign stored in 1 bit and the rest 39 bits for the value. It might also contain two instructions that both have 8 bits for the opcode and the rest for the address. The opcode is simply the type of the instruction represented as binary code such as load, store, or divide. Moving on to the second generation of computers, where transistors were implemented. Computers that time were having magnetic cores memories. And each core is a small metal circle that can store only 1 bit of memory, and that could be magnetized with either 0 or 1. We could do this with the help of the electrical circuit, with electrical wires going through the cores. However, you should know that the process of reading causes the core to be reset to 0, therefore erasing it. It is known as a destructive readout. Also, while not being read or written, the cores maintain the last value they had, even if the power is turned off. Thus, the magnetic core second generation of memory is considered a non-volatile memory. It was until the third generation of computers when the semiconductor memory was introduced, as one chip was about the size of a single core that contains 256 bits, and it was much faster than the core. The two main types of semiconductors memory are read-only memory and random access memory, which you can recognize nowadays as we are still using them in the fourth generation computers and the fifth one, although the semiconductors has been through dozens of generations until now. The ROM and part of the RAM are considered non-volatile memories, and only the DRAM and the SRAM inside the RAM are considered volatile. Now in this part about the CPU's evolvements, we are going to focus on mainly describing the different components of a normal CPU while specifying the major changes in CPUs throughout all the computer generations. Well, in almost all generations of computers, normal CPUs contains the following structural components: a control unit, an arithmetic and logic unit called ALU, registers, and more importantly, a system bus to communicate, containing a control, data, and address buses. A clock is an important component that specifies the speed of each fetch, decode, execute cycle. And also, the CPU might contain multiple cores or caches in modern CPU's generations. To discuss CPU's components, first we take an example of the CPU in the IS structure, the first generation computer. The ALU is responsible for operating on binary data. In other words, when the instruction or the word is loaded to the ALU, it is stored in the memory buffer register, MBR. It is then treated and decoded. The control unit is mainly composed of registers, and it sends control signals through the control bus to request data from the memory. The registers of a control unit are first a PC or program counter that holds next address of the instruction to be executed, an instruction register AR where we load the instruction opcode, the first 8 bits, then the memory address register, the AR where we load the remaining portion of the instruction. And this instruction that we are talking about might be taken from either memory by loading a word into the MBR or the IBR, which is the instruction buffer register, if it is an instruction, not a data. If it's an instruction, not a data. Now, after describing both the ALU and the control unit and the different existing registers and their roles, we are going to look at further details while processing or loading instruction, which is mainly explaining in details the modern fetch, decode, execute cycle in modern CPUs. You should know that compared to old generations of computer, CPUs nowadays have also the memory data register, MDR, and current instruction register, CER, that will explain their role with the help of these steps in front of us. First, we start by the fetching at the PC register that holds the address of the next instruction to be executed. We copy first the address into the memory address register, then we load the content of that location in the memory into the memory data register. Then the same binary code is copied in the current instruction register. Once we finish, the PC is augmented by 1, which means in other words that is now pointing to the next memory location. Now, after describing both the ALU control unit and the different existing registers and their role, we are going to look at further details while processing or loading instructions, which is mainly explaining in detail the modern fetch, decode, execute cycle. You should know that compared to old generation CPUs, nowadays we have also the memory data registers, MDR, and current instruction register, CER, that will explain their role with the help of these steps in front of us. First, we start by the fetching at the PC register that holds the address of the next instruction to be executed. We copy first the address into the memory address register, then we load the content of that location in the memory data register. Then the same binary code is copied in the current instruction register. Once we finish, the PC is augmented by 1, which means, in other words, that now we are pointing to the next memory location. Before doing the same thing again for the next instruction, we have to decode this one, and here comes the role of the control unit. To further understand this part, let's say for example that our instruction is to load the address 5 in the memory that hold a number 13 for example. And this instruction has the address 20. So the address 20 is already in the PC register. We copy the address 20 in the MAR, copy the instruction that the address 20 holds into the MDR, which is loading the address 5, and we do that again in the CER, we load the address 5 and PC now is 24. Now in this case, what we just explained is the assembly language of a computer, a very complex binary language that is close to the machine rather than humans. So we needed actually better understanding languages in order to program the machines. And for this, high-level languages were born, which once we compile or run using a statement or instruction with significant letters, they are simply translated to binary code for the computer to understand. Now the instruction is in CER, but in binary code, so we need to decode it. The decode part is where we take the instruction, look for the first part of it, which indicates the type of the instruction, such as load, store, jump, and the second part which has the address of the data to operate on. For instance, in our example, we load the address 5. So once decoded, we could read what load the address 5 means in binary code. So we actually load or fetch 13 into, first, the memory address register, before immediately placing it in the accumulator, and that is simply the execute part of the cycle. Keep in mind that the ALU comes in play if the next instruction is add, for instance. We get the content of the accumulator and add to it whatever value of the address that came with the add instruction, to finally overwrite and store the final value back into the accumulator register. Remember that this is done very fast. In fact, it is binary of instructions per second, nowadays with clock speeds that could reach 5 GHz. Now going back to our largest prime number problem, and after discussing the improvements of the memory being fast and having greater capacities all over the generations, as well as other major computer technologies such as moving from vacuum tubes to microprocessors nowadays, we can discuss and look at our real-life mathematical problem and demonstrate the effectiveness of recent generation computer when trying to solve it as opposed to earliest generations. Well, the first computer to find the largest prime number that time was the SWAC, a first-generation computer which was the fastest computer in the world when it was created, until the IS computer was completely done in 1952. Researchers also used other powerful improving computers those days such as BESC or IBM 7019 to compute the largest prime number. You can find in the following table different records of the largest prime numbers as well as the machine used and the prover. Moving on to the next question, we will now try to answer an existing interesting computer program issue. Well, we know that nowadays CPUs are decreasing in volume, becoming much smaller, certainly having more technology than the older generation of CPUs. But what are some of these technologies, and most importantly, what are the trade-offs for building more powerful CPUs? What do you actually sacrifice in order to do that? What is the result that you get? Before moving to answer these questions, you should understand the basic computer concept or model called the von Neumann model that almost all computers and general-purpose computers are based on. In front of us, we have a picture showing the general structure of a von Neumann-based computer. More specifically, it is the IS structure example, a first-generation computer. And as you can see, it is composed of three major parts, which are the main memory, to distinguish it from other memories in the computer, the ALU or the arithmetic and logic unit, a control unit and registers that are located inside the central processing unit, and finally the IO's device. You should know that the main memory holds both the instruction and data. The ALU is the one responsible of operating on binary data. When the CPU wants to access memory values, it will send the address of the first location of the desired values to the memory, and the memory will return the n bits value stored there. Think of it as an array when you just give it the first index location to get or return the full array. However, we previously mentioned both that the data and the instruction are stored in the memory, and both in binary code. So how can we distinguish between them? Well, the answer is that we can't by looking only at the binary code. It is how they are used and more precisely where they are loaded. If it's data, the CPU will read it in specific registers in order to operate on it. And if it's an instruction, it is used and loaded into the control logic. Also, keep in mind that the von Neumann model executes programs following the fetch, decode, execute cycle, the one explained before. In this example, we discussed the IS computer example. However, all next generation CPUs have actually the same structure. They only implement and use more advanced parts such as caches and some design technologies like multi-cores, pipelining, branch prediction, or speculative execution. Well, let's now have a look at an example of a CPU design technology and its trade-offs using multi-cores. First, to better understand what do we mean by a trade-off, think of it as the battery life that you sacrifice in order to have better graphics, or simply the trade-off between getting a good sleep and staying up late night to finish a research project. But what is a core? A core is the brain of your computer. In other words, it is the smallest physical unit capable of processing instructions inside the CPU. It is basically a CPU in the IS structure, for instance, containing all its components, the ALU, control unit, and registers. And later, at 1989, the concept of caches was implemented as well. Now, the multi-core concept is simple. It is the idea of putting on a single integrated circuit two or more cores. It was first implemented in 2005 with Intel Pentium D processor. But what did we get from that? What was the advantage of putting two cores instead of one? First, concerning the limitations, they are relatively good trade-offs. For instance, we could mention just faster battery drainage and that the speed is not doubled even when multi-core technology was implemented. In fact, the advantages are interesting. Some of them might be that it allows PCs to run multiple processes at the same time with greater ease, increasing the performance when multitasking or under the demands of powerful apps and programs, as well as less power consumption. Increased handling of interrupts is also a great feature that we will discuss and explain in the next slides. However, one of the major causes that was the reason for moving to implementing multi-core technology at the industry level in recent processor is because they generated less heat. Well, how is that? We need first to understand the concept of the clock speed. In a simplified way, it measures the numbers of fetch, decode, execute cycles that your computer can perform per second. Keep in mind that when the clock speed increases, it generates more heat in the system, same relationship as a core at a high speed and the increasing temperature of the engine. Nowadays, computers reach the maximum clock speed, therefore we needed to find another way to improve the processing speed of a CPU. And that is why we created and implemented the multi-core technology. And once launched, computer had better heat distribution. CPUs industries gave up on trying to increase the clock speed and shifted to multi-core design. Today, modern CPUs have between 2 and 64 cores, with most of them containing 4 to 8. We previously mentioned that one of the advantages of the multi-core design technology was the ability of handling more interrupts. First, what is an interrupt? Well, it is when a signal is sent from a device or software to the operating system or the OS. Think of the OS as a medium between you as the user and the CPU. When you give some input via input devices, the input is directed to the CPU as per the pre-assigned commands in the OS. Then, when the processing is done in the CPU, it sends back the output to the output devices, such as your screen after moving your mouse or also when you press the key on a keyboard. A hardware interrupt is generated. There exist different classifications of interrupts, but we can agree on the following 4 types. First, program interrupts. It is when the CPU is interrupted if a division by 0 occurs or when the user is trying to access non-allowed memory space. Second, a timer interrupt, the most important one for the OS, which is emitted at regular intervals by the CPU. and it performs certain functions such as keeping your computer dates and time updated. Third, the I/O interrupts, and these are generated by input-output devices, same example as moving the mouse and key press on a keyboard interrupt. Finally, hardware failures are occasional, but it is when a power failure happens, for example. Now, after discussing these interrupts and the classification of these interrupts, you will be able to notice why multi-core CPUs could handle more interrupts. Well, simply because an interrupt is directed to one and only one core. Having multiple cores will make the handling task easier and faster. So we mentioned that interrupts are important because they are giving the user better control over the computer. Without interrupts, a user may have to wait for given tasks that have higher priorities over a simple key press or paper jam in a printer. The length of this pause may be on the order of many hundreds or even thousands of instruction cycles that do not involve memory. Clearly, this is a very wasteful use of the processor. We need therefore to handle these interrupts using an interrupt handler. But how does it work? Well, interrupt handlers are special blocks of code associated with a specific interrupt condition. For every interrupt that could happen, we have a block of code that needs to be launched, and the address of this code is stored in the memory. The role of the interrupt handler is to service the device and stop the device from interrupting anymore. It is first done in software in operating system. You should know that modern CPUs provide a mechanism to allow portions of the software to operate with different levels of privileges. There are 4 rings numbered from 0 to 3. Programs executing in ring 0 have the highest privileges and are allowed to execute any instructions or access any physical resources such as a memory or an I/O device. This is accomplished by setting the current privilege level or the CPL register of these processors to 0. User programs are usually operating on a ring 3, and if the program tries to access a protected resource such as an I/O device, an interrupt takes place. Therefore, the steps numbered from 3 to 6 needs to be executed. Steps 1 and 2 are an interesting advanced procedures which are obtaining and assigning the IRQ number used to distinguish between different interrupts coming at the same time, and also step 2, which is switching to kernel stack. The important actions are the following ones. First, the CPU stops whatever it's doing and it needs to save the program state, mainly through registers and flags, so that the CPU resumes executing the process after interrupt handling is finished. Then the interrupt handler is loaded to the CPU from the memory so that the OS is capable of handling it in step 5, or launching the code of the interrupt handler, which is mainly doing some tasks such as saving information or communicating with I/O devices. Finally, after the interrupt is being handled, all earliest flags and registers are being restored and the CPU resumes whatever work it was doing. Moving on to 1990s processors, CPU's features were improving. Clock speed was almost doubling after each generation, as well as bus width and transistors. The feature size was decreasing because that was the need, smaller but powerful processors. Caches also were developing in terms of memory. In fact, a new technology was implemented for caches, which was the level of it. L1 caches are the closest for the CPUs, L2 caches are relatively far from the CPUs. Slow as opposed to the L1 caches, but still faster than the main memory. Now concerning the last table of recent processors, an interesting situation happened. The clock speed was not doubling or increasing anymore. We mentioned previously that the main reason for that was the heat that it generated. Therefore, we needed a new technology that could help us improve the speed of the processor, and that was the multi-core technology as previously stated. As you can see, the Core Duo microprocessor in 2006 had 2 cores instead of all the previous one that had only 1. Now we are moving to the last part of our presentation, and we are going to illustrate and explain how a CPU will communicate with different I/O devices, for both older and modern ones. But of course, following the same analogy as the previous two questions, we need first to talk about and comment relevant topics, and one of them is discussing the technology trends in the different generation of CPUs. In fact, since the third generation of computers, the one with integrated circuits, CPUs have evolved and developed several technologies. For instance, in front of you, in these tables, the Intel CPU's trend technology, developing each feature from one processor to another. The first commercially produced microprocessor was Intel 4004 in 1971. It had a clock speed of 108 kHz, a bus width of 4 bits, which basically means that only 4 bits of data could be transmitted to the CPU through the system bus. It had around 2,300 transistors, and almost every component of it had a size of 10 micrometers, with 640 bytes of addressable memory. Furthermore, and throughout the years were made new microprocessors such as the following 8008 trend that has the same clock speed, a double bus width, smaller size of components but a huge addressable memory increase. The number of transistors in all next processors are following Moore's law, which states that the number is doubled around each 2 years. The observation was posited in 1965, but it had been the case since the Intel 4004 microprocessor creation. Now, in order to increase the speed of the CPU, Intel 8080 was built with the faster clock speed, and each feature was improved. However, from the 8086 microprocessor and above, the focus of the company was to create commercially cheap and approved processors, rather than building only powerful ones. Therefore, CPUs were having different ranges of clock speed. For instance, 8086 processor with 5, 8, or 10 MHz clock speed. And same goes for the bus width that was 16 bits for the 8086, but switched back to only 8 bits of the 8088 trend. The 8086 had also improved the registers in terms of number and performance. Now, if we look at the next table, we could just extract the same observation as the previous table. Different features and technologies improved, component size became smaller, transistors were doubling as well as the clock speed. However, what is really interesting is the birth of a new technology called caches. It was until the late 80s with the 486 TMDX CPU that caches were developed. They are small amount memory. It is used to temporarily hold data and instruction for the CPU to reuse, and it is closer to the CPU than memory, therefore faster speed CPUs were created. Before directly moving to answering our question, another relevant question would be the understanding of the speed difference between not only CPUs, components, but also any computer component. For instance, what makes a CPU or a RAM faster, or in a more general way, how do you decide which computer to buy? Concerning the CPU speed, we basically discussed throughout the two previous slides how can we improve its speeds. A CPU with multiple cores, a big clock speed, widest bus, and an improved cache memory might be the fastest. Moving on to the RAM components, you should know that with the faster RAM you increase the speed at which memory transfers information to other components. And in order to obtain a faster one, we'll just need to improve the capacity of it. For instance, buying a 16-bit RAM instead of an 8-bit RAM. However, keep in mind that you absolutely won't increase your system speed. In fact, the more RAM you have, the more application you have and you can open simultaneously. Finally, the hard drive could also improve the speed of your personal computers. For example, your computer needs to read stored data and it will need the hardware. So it must retrieve bits of information from a disk that spins at 1,000 revolutions per second. The hard drive speed determines how long it takes an application to access the data it needs. If you need a computer that retrieves data very fast, you need a hard drive with faster speed then. Finally, now we can move directly to answer the question of how CPUs communicate with I/O devices. In a very simple way, as far as the CPU is concerned, I/O devices are only external instructions. In old CPU's generations and old computer generations, the I/Os were directly connected to the CPU, meaning through the bus directly. Nowadays, devices are plugged into a controller and only the controller is connected to CPU through the bus system. In fact, the communication between CPU and input-output device is implemented using an interface unit. In a computer system, data is transferred from an input device to the processor and from the processor to an output device. Each input and output device is provided with the device controller, which is used to manage the working of various devices. Actually, the CPU communicates with the device controllers for performing the I/O's operations. In a computer, the interface unit works as an intermediary or a medium between the processor and the device controller of multiple devices. The interface unit accepts the control command from the processor and interprets the commands so that they can be easily understood by the device controller for performing the required operations. Hence, the interface unit is responsible for controlling the inputs and output operations as well.